At the scene of a fire, the fire pumper is your department's main defense against disaster. Effective fire suppression demands that these apparatus be operated properly and efficiently to supply the water necessary to meet the fire service goals of saving lives and property. To operate this sophisticated equipment and to qualify as a fire pumper operator, you need to understand all the gauges and controls used to monitor and operate the pump, how to position the fire pumper to a given source of water for effective and safe operation, and you need a thorough knowledge of pump operation to ensure that water is delivered quickly and effectively to meet the demands of any fireground situation. In this program, we will identify the pump gauges and controls, demonstrate how to properly position a fire pumper to various sources of water, and describe 3 methods of power transfer from the vehicle engine to the pump. The gauges and controls of a fire pumper are located at the pumping station of the apparatus. Normally, the pumping station is located on one side of the pumper, or at the front of the vehicle on apparatus with front-mount pumps. But some pumpers may have the pumping station located midship with the pump panel facing the back of the cab. The type, number, and location of gauges on the pump panel may vary from apparatus to apparatus, but generally you will find pressure gauges to monitor water flow through the pump, automotive gauges to monitor the operating condition of the engine, a fuel gauge to monitor the fuel level in the fuel tank, and a water level gauge to monitor the water level in the booster tank. Pressure gauges are used to monitor the flow of water during a pumping operation. These gauges are one of 3 types: vacuum gauges, positive pressure gauges, flow meters, or compound gauges. Vacuum gauges measure any pressure below atmospheric pressure. The calibration of these gauges will be in inches of mercury, which is sometimes referred to as inches of vacuum. The vacuum gauge is used when priming the pump and during a drafting operation. During the priming or drafting process, the vacuum gauge tells you when the correct amount of vacuum is reached for drawing water into the pump. The amount of vacuum required for different pumping conditions or priming systems may vary. It is your responsibility to learn and understand the vacuum requirements for the different pumping conditions you may encounter at the fireground and for the priming system of your pumper. Positive pressure gauges found on an apparatus are used to indicate pressure greater than atmospheric pressure. These gauges are calibrated in pounds per square inch. A fire pumper normally has a positive pressure gauge to monitor water pressure at the suction side of the pump, one to monitor total water pressure delivered at the discharge side of the pump, and, on some apparatus, one to monitor water pressure at each individual discharge gate on the pumper. Having individual gauges at each discharge gate allows you to adjust the gates to supply each hose line with the optimum pressure, to increase operating efficiency and greater safety for the nozzle operators. Many fire pumpers use flow meters instead of positive pressure gauges at each discharge gate. These meters work under positive pressure and measure the flow of water in gallons per minute instead of pounds per square inch. Flow meters can simplify your duties at the fireground by reducing the number of manual hydraulic calculations needed to produce an effective fire stream. With a flow meter, the flow of water from the pump discharge is the same as the flow of water out of the nozzle. Manual calculations for friction loss or hose layout are not necessary. To maintain the proper quantity of water to the nozzle, watch the flow meter at the discharge, and adjust the speed of the pump with the engine throttle to maintain the required water flow. Flow meters do not eliminate the need to understand firefighting hydraulics or the necessary math calculations used at the fireground, but they will reduce the number of calculations you need to make. The compound gauge is another gauge found on the pump panel. This gauge is designed to measure incoming pressure, both positive and negative, on the main pump. The zero on a compound gauge actually represents atmospheric pressure, or 14.7 pounds per square inch. A compound gauge is calibrated in pounds per square inch for pressures above zero, and in inches of mercury for pressures below zero. The needle of the gauge rotates clockwise for positive pressures and counterclockwise for negative pressure. During a pumping operation, this gauge indicates the condition of the water flow from the water source. Positive pressure is registered when pumping from a hydrant or pressurized source, and inches of vacuum when pumping from a draft or static source of water. To protect the engine and make sure it is operating at peak performance during the pumping operation, there is a set of automotive gauges mounted at the pumping station. These gauges usually include a tachometer, oil gauge, and engine temperature gauge. The tachometer indicates the speed of the engine crankshaft in revolutions per minute. A tachometer may also have calibration marks to indicate engine speeds required for corresponding pump capacities. A manufacturer's chart, based on hose layout, nozzle size, and water source pressures, must be used when using the calibration marks of the tachometer to monitor the capacity of the pump. You need to know the manufacturer's performance data for your vehicle's engine and pump, and monitor the tachometer to operate them at their maximum efficiency, while making sure they are operated within the manufacturer's operating limits to prevent damage. The oil gauge on the pump panel indicates whether or not the engine lubricating system is operating properly. This gauge is critical for preventing damage to the engine. Friction caused by insufficient oil or a failure of the engine lubricating system can quickly destroy the engine. Monitor the oil gauge closely during the pumping operation. If the pointer fluctuates rapidly, or if the pressure reading is below the operational level specified by the manufacturer, you should shut down the engine immediately. Continued operation could result in permanent damage to your engine. Some pumpers may have a low oil pressure shutdown switch that shuts the engine down automatically if oil pressure falls below manufacturer's operating pressure. The engine temperature gauge is another automotive gauge found at the pumping station. The temperature gauge indicates the operating temperature of the engine in Fahrenheit or Celsius. This gauge should be monitored closely so that the engine operates at the proper operating temperature for maximum efficiency and to protect the engine from damage due to overheating. Overheating can cause a breakdown in the lubrication properties of the engine oil, resulting in damage to the internal parts of the engine by friction. Proper operating temperature for most engines is usually between 160 and 190 degrees Fahrenheit. Remember, during a pumping operation, the engine does not have the benefit of the airflow available when driving. To compensate for the loss of airflow, most fire pumpers have an auxiliary cooling system. By watching the temperature gauge closely, you will know when or if you need to use the auxiliary cooling system to protect the engine from overheating. The fuel gauge is another gauge used to monitor the automotive system. During a response, a pumper may be required to operate at full capacity for hours. Monitoring the fuel gauge keeps you informed of the fuel level in the fuel tanks and tells you when to call for refueling if the fuel level falls below a fireground operating level set by your department. Most pumpers have a booster tank to supply water to attack lines while the pumper is being connected to the water supply. There is a water level gauge or series of lights to monitor the water level in the booster tank. The water level gauge or series of lights will inform you of how much water is in the booster tank. If you use the booster tank during a response, always refill it immediately at the nearest water source or upon returning to the station so it is ready for the next response. Fill the booster tank until the water level gauge registers full and water runs out of the booster tank overflow. Various valves and controls are also located at the pumping station for operating the pump and controlling the flow of water from the water source through the pump and to the nozzles. Understanding the purpose of these controls and using them skillfully is necessary to ensure that water from the pump is delivered quickly and efficiently to the firefighters at the nozzles for effective fire suppression. The number and location of the controls depends upon the manufacturer, but certain controls are usually found on all pumpers. Controls for operating the pump usually include intake or discharge valves, drain valves, a transfer valve on an apparatus with a multi-stage pump, controls for the priming device, controls for the pressure control device, engine throttle control, controls for the auxiliary cooling system, and controls for the booster tank. The intake and discharge valves on a fire pumper control the flow of water entering or leaving the pump during a pump operation. Intake valves control the water entering the pump. Discharge valves control the water leaving the pump. These valves are designed with a locking device so that you can lock them at any position to specifically regulate the water flow for the conditions at the scene. Most pumpers have valves designed for push-pull, or up and down, or side-to-side operation. Push-pull valves have a T handle that pull out to open the valve and push in to close. To lock a push-pull valve in position, move the T handle to the desired position and rotate the handle 90 degrees. Fire pumpers with up and down or side-to-side valve operation have quarter-turn valves with handles that are rotated up and down or side-to-side to open and close. These valves are locked in position by turning the knob on the handle. Always open and close discharge valves that control the flow of water to the hose lines slowly. Opening a discharge valve too quickly will cause a drop in pressure to other hose lines and cause surging. Closing a discharge valve too quickly may cause water hammer that can result in damage to hose lines, pump, or water mains. Your pumper will also be equipped with drain valves. Controls for the drain valves are usually located low on the pump panel. Normally, there are drain valves for the intake and discharge lines and the main pump. The purpose of the drain valves is to relieve the water pressure in the pump and pump lines, to make uncoupling hose lines from the pump easier after a pumping operation. Also, drain valves are used to drain the pump and its piping during the winter to protect them from freezing. A transfer valve will also be found on apparatus with the series parallel centrifugal pump. This valve is used to control the pressure or volume of water being pumped during a pumping operation. The valve has two settings, which may be designated as pressure volume or series parallel. Series designates the pressure position, and parallel the volume position. To create higher pressure, place the valve in the pressure or series position. In this position, the valve channels water directly from the discharge outlet of the first stage of the pump to the inlet eye of the second stage, where water pressure is increased, then discharged to the discharge outlet. To increase volume, place the valve in the volume or parallel position. The valve channels 1/2 of the total water available to each stage of the pump. Each stage operates as a single-stage pump that increases the volume by discharging the water to a common discharge. Care must be taken when switching from one setting to the next. Use the throttle control to slow the pump and lower the water pressure. This is especially critical when switching from volume to pressure. Switching from volume to pressure when the pump is running at capacity may result in a pressure surge in the hose lines that may jeopardize the safety of the nozzle operators or damage the pump. Controls for the priming system are also on the pump panel. Whenever you must draw water from a static source, such as pond, lake, or stream, you need to use the priming system to prime or get water to the main pump. A centrifugal pump has an open waterway from suction to discharge that does not allow it to create a vacuum and prime itself. Only after a centrifugal pump is filled with water and running can it maintain the vacuum necessary to operate. There are different types of priming systems, but they all perform the same function. They draw air from within the pump to create a vacuum or lower pressure that allows the atmospheric pressure on the surface of the water to force the water through the suction hose and into the pump. Depending on the priming system of the pumper, there will be a switch marked on or off, a lever that must be pulled, or a button that is pushed to activate the priming device, and a priming discharge valve that discharges water to indicate when water has reached the pump. If the priming discharge valve on the pumper is manual, you must open it during the priming procedure and close it once the pump is primed. Automatic discharge valves will open and close automatically during the priming process. If the pumper is equipped with a positive displacement priming device, there may also be a knob or valve to the priming oil tank. This valve must be opened during the priming process to lubricate and seal the priming pump and make it more efficient in creating a vacuum. To operate the priming device, first, open the intake valve you are going to use for suction. Next, make sure all other valves and openings of the main pump are closed to form an airtight chamber. Use the priming control and activate the priming system. Watch the vacuum gauge to see that a vacuum is being formed, and wait until water flows from the priming discharge valve, indicating that water has reached the pump. Do not shut off the priming device too soon. During the initial stage of priming, there will be air escaping with the water from the primer discharge. If the priming device is shut off too soon, air will be trapped in the pump, affecting the pump's performance, and may even cause the pump to lose its prime. Conditions at a fire ground can change quickly. A pump operator seldom knows in advance when a hose line will be shut down. To prevent excessive pressures from developing during the pumping operation, most pumpers are equipped with a pressure control device. The purpose of a pressure control device is to protect your nozzle crew from injury and to prevent damage to the pumper's hoses, pump, and engine from the sudden increases in pressure. To relieve excessive pressure, an apparatus is usually equipped with either an automatic relief valve that opens as a bypass between the suction and discharge side of the pump, or a pressure-operated governor that controls the speed of the engine to slow the pump and decrease the amount of water pressure. There are many different manufacturers of governors and relief valves, and many differences in the way each operates. As a pump operator, you need to become familiar with the pressure control device on your apparatus. The controls for a pressure relief valve usually consist of a four-way valve to place the system on or off, and a control handle or wheel that determines the pressure setting for the relief valve during operation. There may also be a pilot light that comes on when the relief valve opens. To set a relief valve, bring the pump to a desired pressure, for example, 150 pounds per square inch. Make sure at least one discharge line is open, and turn the control handle counterclockwise until the pump pressure begins to drop and the pilot light comes on. The pressure drop and light indicates that the relief valve has opened and is bypassing water. Next, turn the control handle or wheel in a clockwise direction until the original pressure of 150 psi is reached and the light goes out. The relief valve is now set and will operate anytime the pressure exceeds this set value. Remember, you must reset the relief valve each time the operating pressure of the pump is changed. A pressure governor works on the principle that a reduction of engine speed decreases the pump speed, which results in a reduction in water pressure. The controls for a pressure control governor usually include a pressure control knob and an actuator or control valve. The linkage of a pressure control governor is connected to the throttle of the engine. When the actuator is engaged, the system responds to excessive pressure by moving the linkage and slowing the engine down, which slows the pump and reduces excessive water pressure in the pump and hose lines. To operate a pressure governor, the pump should be running and flowing at desired pressure and quantity, with the hose lines open. For example, if the desired pressure is 150 psi, turn the pressure control knob until the pump is pumping slightly above the desired operating pressure. Activate the governor by opening the governor valve or pressing the actuator. Turn the pressure control knob back and reduce discharge pressure to the original pressure of 150 psi. The governor is now set and will increase or decrease the speed of the engine to maintain the preset pressure. On some apparatus, you must be careful. A loss of water at the water source will cause the pressure control governor to increase the speed of the engine to maintain the set pressure. Without an intake source of water, the action of the governor may cause the engine to overspeed, which could damage the engine or pump. Monitor the system closely. If the engine increases speed without an increase in pressure, manually slow the engine with the throttle control. The throttle control is a remote throttle that allows the speed of the engine to be controlled at the pump panel. The speed of the engine determines the speed of the pump. Adjusting the throttle control allows you to increase or decrease the flow of water to the hose lines. During operation, watch the discharge gauge and adjust the throttle to maintain the specific water flow required by the conditions at the fireground. The pumping operation may require the engine to run at full load for an extended period of time. Under these conditions, the normal cooling system of the engine may be inadequate to keep the engine from overheating. Raising the hood of the apparatus may help by providing better air circulation and allowing engine heat to dissipate more quickly. If not, most apparatus have an auxiliary cooling system to protect the engine from overheating. This system acts as a heat exchanger. Cool water from the pump circulates through a coil, while the hot water from the radiator circulates around the coil. Heat from the radiator water is transferred through the coils to the cooler pump water. Normally, there are two valves that control the auxiliary cooling system. An auxiliary cooler valve that allows water from the pump to circulate through the heat exchanger, and a radiator fill valve that allows water from the pump to fill the radiator. If the temperature gauge indicates that the engine is overheating, open the auxiliary cooler valve slowly. Watch the engine temperature gauge until the engine temperature returns to the proper operating temperature. Be careful not to open the auxiliary cooler valve too much, too fast. Opening the valve too much, too fast may cool the engine too much and prevent the engine from running efficiently. The radiator fill valve admits water from the discharge of the pump directly into the radiator. This valve should be used only as an emergency measure to cool the engine. A sudden surge of water from the pump at discharge pressure could cause the radiator to burst. If you must use the radiator fill valve, open the valve slightly until water flows from the overflow piping of the radiator. Leave the valve open until the temperature of the engine returns to normal, then closed. The booster tank valves are also located on the pump panel. The tank-to-pump valve allows water to flow from the tank to the pump during a booster pumping operation, and The tank-to-fill valve allows water to flow from the discharge piping of the pump through the tank for refilling. These valves can also be used to cool the pump if needed. Opening each valve will circulate water from the booster tank through the pump and back to the tank to keep the pump cool. As an operator, you must be able to effectively position a pumper to various sources of water. Positioning the pumper requires an understanding of fireground operations and strategies, good judgment, skillful handling of the apparatus, and the ability to assess the situation and make quick decisions. The assessment may be made by you or by the incident commander, but should include any variables that may jeopardize the safety of your crew, the pumper, or the ability of the pumper to attack the fire effectively. These variables may include, but are not limited to, exposures to the fire, wind direction, power lines, terrain, traffic flow, and the type and capacity of the water source and its proximity to the fire. Available sources of water generally fall under two categories: from a hydrant or pressurized source, or from a draft or static source. To position the pumper to a hydrant, look for a hydrant that best fits the needs of the fire attack based on the initial assessment. There are different procedures for positioning a pumper to a hydrant. Two common methods are the forward lay-in and the reverse lay-in. To perform a forward lay-in, come to a complete stop at the hydrant. Have the hydrant operator exit the pumper with the tools necessary to complete a hydrant connection. The hydrant operator then pulls the hose from the hose bed of the pumper and makes a loop around the hydrant, planting a foot on the end of the hose to anchor the supply hose to the hydrant. Make sure no part of the hydrant operator is between the hose and the hydrant. Then, drive the pumper forward to a predetermined position to fight the fire, laying the hose from the hose bed as you go. Using the reverse lay-in method, if flexible hose is used for the intake connection, you must know the length of the hose to properly judge the distance from the hydrant to spot the pumper. Most flexible hose sections are 10 to 25 feet long. On the approach, stop the pumper with the intake a few feet short of being in line with the hydrant outlet. Stopping short of the hydrant outlet allows the intake hose to be slightly curved and will prevent kinks in the hose after pressure is applied. Turn the wheels of the pumper into the curb at a 45-degree angle. Turning the wheels into the curb will allow you to make adjustments in distance between the intake of the pumper and the outlet of the hydrant by driving forward or backward. Make sure your pumper is close enough to the hydrant so that the suction hose can touch the ground. If the hose forms a bridge, undue strain on the inlet and outlet couplings will result, which may cause the hose to pull loose from the coupling or burst. Using a non-collapsible hose during a reverse lay-in requires a slightly different procedure. Stop the pumper with its intake just short of the hydrant outlet. Attach the hose to either the pumper intake or the hydrant outlet. Have a firefighter bend the hose while you drive forward to make the connection. Front or rear intake connections will follow the same procedures, except you need to angle the front or rear intake inlet of the pumper in the direction of the hydrant. No matter what connection you use, remember, your pumper is only part of an overall firefighting effort. Position your apparatus as close to the curb and the hydrant as possible to allow other response vehicles passage to perform their duties. To position a pumper to draft water from a static source, place the pumper as close to the water supply as safety will permit. Placing the pumper close to the water source allows you to get the most capacity from the pump. Along a stream, lake, or pond, choose an area that is relatively flat. Inspect the ground to make sure it is solid enough to support the weight of the vehicle before you commit it. If possible, position the pumper with the pump panel away from the water, so that the suction hose will not interfere while you operate the pump controls. Making the hard suction layout for drafting normally requires the cooperation of the entire engine company. A section of non-collapsible hose is usually 10 feet in length, making them heavy and bulky. To determine how many sections are required, estimate the distance from the pump intake to the surface of the water. Remember, friction loss in any lift more than 10 feet will reduce the capacity of the pump. Add a minimum of 2 feet to submerge the suction strainer to prevent whirlpools and eddies from forming. Whirlpools and eddies can reduce the performance of the pump, or even cause the pump to lose its prime. Couple the sections together. Use a rubber mallet to tighten the coupling lugs at each connection for an airtight seal. Attach a rope to the intake strainer to hold it off the bottom when submerged and aid when lowering and raising it from the water. Next, connect the suction hose to the intake of the pumper and tighten with a rubber mallet. Use the rope to lower the strainer into the water. You can adjust the depth of the strainer with the rope and tie it off to the pumper when it is at the correct depth. If a ladder is available, another method is to lay the suction hose on the ladder and adjust the depth of the suction hose with the end of the ladder. Engine power is transferred from the pumper's engine to drive the pump. Generally, this power is transferred from the engine to the pump in one of 3 ways: from the front of the crankshaft, from the drive shaft, or from a power takeoff. Power from the front of the crankshaft is used to drive front-mounted pumps. A clutch lever mounted next to the pump is used to transfer the engine power to the pump. To engage the clutch, reduce the speed of the engine to at or near idle with the throttle control, and slowly move the lever to pump. Use caution when engaging the clutch to protect the engine and the pump from damage. If the engine speed is too high or the clutch engaged too quickly, it may cause irreparable damage to the clutch assembly of the pump drive. Drive shaft operation transfers engine power through a pump transmission located in the drive line between the engine and the rear wheels. This type of power transfer is used to power midship pumps. To engage, make sure the engine is at or near idle to protect the engine and pump transmission gears from damage. Shift the pump lever to pump and put the engine transmission in 5th gear. A power takeoff, or PTO, is another method of transferring power from the engine to the pump. The PTO unit is normally located on the side of the engine transmission. All pumpers with automatic transmissions have PTO-driven pumps. To engage the pump, shift the pump shifting lever to pump. Operating a PTO-driven pump does not affect the vehicle transmission. The fire pumper is the most important weapon in your department arsenal for fighting fire. Evolved from the need to move water efficiently and effectively, the fire pumper has become a very complex and sophisticated piece of equipment. Operating this complex equipment is a challenge that requires exceptional knowledge and skill. To meet this challenge and to qualify as a fire pumper operator, you need to thoroughly understand the pumper's gauges and controls, how to maneuver and position the pumper to a source of water to provide the maximum safety for your crew, protection for your apparatus, and effectiveness against the fire. You will be rewarded for developing the expertise necessary to operate a fire pumper efficiently and effectively by knowing that your knowledge and skill is instrumental in saving lives and property at the scene of a fire.